Hi, in this video I want to talk about how to find the inverse of a trigonometric function. So if we were given some trig function like this and asked to find the inverse function there, how would we go about doing that? The process here is exactly the same process we learned in algebra. In algebra we learn how to find the inverse of any function. We're going to apply those same steps here just to our trig function. So let's take a step aside and remember how to do that. Here we've got an algebraic function, all right, 3x plus 2, and we're asked to find the inverse. So the first thing you need to do is you need to ask yourself, do you even have an inverse to begin with? Is your function 1 to 1? If you recall from algebra that a function has to pass the horizontal line test. Remember what an inverse is doing. If we think about the domain of a function in a range, and let's say a is assigned to 1 and b is assigned to 2. So f of x, the function, is taking things from the domain and assigning them to the range. The inverse function is going the other way. It's taking things from the range and sending them back to the domain, or telling us where they came from in the domain. Well, we want this guy to be a function. And remember, to be a function, isn't it the case that every input has to go to exactly one output? Okay, well in this case the inputs, they're coming from the range, right? For this function they are, for my inverse function. And so we need each of these guys to be assigned to precisely one of these guys. And that is accomplished by having a 1-to-1 function. So this function we're given is 1 to 1. If we were to graph this function f of x, it's a linear equation, right? We've got a y-intercept of 2 and a slope of 3. So we would look something like this. You're 1 to 1 if you pass the horizontal line test, meaning that any horizontal line you draw corresponds to only one input, or it intersects the graph only once. And what that tells me is that by picking some horizontal line, what you're actually doing is you're picking something in the range, and you're making sure that it is assigned to only one thing in the domain. So that's the whole point of the horizontal line test, is making sure that when you run the function backwards, that it is actually a function. Okay, so that was maybe more than we needed to know. In short, does it pass the horizontal line test? If yes, good, move forward, you're 1 to 1. If not, hope is not all lost. There are things we can do in order to make a function that's 1 to 1, and then we can solve from there. So this function, again, my line is 1 to 1, and so let's run through the steps now of what it takes to find an inverse. So I'm going to just do these steps as they're written. Step 1, it says replace f of x with y. So I'm going to look at my function here and replace the f of x with y and just rewrite things. And this is purely to make our written work a little easier. Number 2, switch the places of the x's and the y's. So swap out x's and y's. And what you're doing here is you're actually kind of changing your inputs to outputs, or outputs to inputs, I guess, however you want to think about it. You're beginning to find that inverse function. Step 3 is where you actually do it. Now you solve for that y value. And by taking this equation and solving it for y, you are unwrapping the thing, and you're telling us where those original outputs, or the guys in the range, where they came from, what domain elements. So number 3 is the step that actually finds the inverse. So if you want to solve for y, let's bring the 2 over. Then let's divide by 3. Now that is your inverse, right? So step 3 finds it. So step 4, they say, okay, well, let's just go back to function notation. Let's use more proper mathematical notation. And we could say f inverse of x is x minus 2 over 3. There's our inverse function. And so we can apply those same steps to our trig function. Let's talk about one more thing here real quick, and that's the domain and range. So if we look at our original function, this line, and we think about the domain and range, this isn't going to be a great example of this, but it's a line. So this line I've drawn here goes forever left and right, forever up and down. The domain is negative infinity to infinity, and so is the range. It's all real numbers. Well, if you compare that to my inverse function, this too is a line. Right? If I were to distribute that 3, I could write it as 1/3 x minus 2/3. So there it looks a little more like a linear function. And so this also has domain and range of negative infinity to infinity, negative infinity to infinity. So this isn't showed off really well here, but what's really happening is the domain of f is flip-flopping with the range of f inverse. Or rather, they're the same thing. The domain of f is the range of f inverse. The domain of f is this set, and that's also the range of f inverse, since f inverse starts over here. And likewise, the range of f is the same as the domain of f inverse. And that's really handy to remember. It's really important to remember that when it comes to finding domain and range, especially with trig functions, it could be helpful. So let's go back to our trig function here. Find this inverse. First things, is this invertible? Is it 1-to-1? Right off the bat, no, it's not. If you look at sine, a sine wave does this, right? So that thing fails the horizontal line test miserably. But that's why inverse trig functions are restricted. We know for sine inverse, we should restrict this thing from negative pi over 2 to pi over 2, or negative 90 to 90. Because if we're only looking over that area, that little green region there, that dude is 1-to-1, and therefore we can talk about an inverse there. And that restriction of negative pi over 2 to pi over 2, that applies for anything inside my trig function. So I'm just going to put a little note onto the side when it comes to finding the domain of f. I should specify which function, my original function. I know all that stuff crammed in between, or within that trig function, is between negative pi over 2 and pi over 2. And I know I'm working in radians because I see no degree symbols here. So that's the default assumption is radians then. Okay, so we've got some sort of restriction established. In other words, we know that over this region, and later I'll just move the 2. Well, let's go ahead and do it now. Let's subtract 2 from all 3 sides. Let's get our answer a little better. The domain of this thing is pi over 2 minus 2, and this is negative pi over 2 minus 2. So x, our inputs are in between those two values. So there's the domain of f, which means it's also the range of f inverse. But yes, 1-to-1 on this interval here. All right, so first step, replace f of x with y. Second step, switch the x's and the y's. Third step, solve for y. And this is when you are actually unwrapping and finding the inverse function. So the first thing I'll do is move that 5 over, just like we did with the algebra case. I'm going to go ahead and divide by 3, get that 3 over to the other side, so I'd have x plus 5 over 3 is sine of y plus 2. And now I need to free up the y value there. I need to dig it out of that trig function. And so I could do that by switching to inverse notation. Remember, this must be some angle because it's embedded in the trig function. This must be some ratio because it's equal to a trig function. And so if I switch to inverse trig notation, which I'm allowed to do because I know I'm invertible here, I could say sine inverse of this ratio would be equal to this angle. And lastly, I could just subtract the 2 over. So I get sine inverse x plus 5 over 3 minus 2 is y. That's it. That's the inverse. Step 4 was go back to function notation. So we could state this a little more formally. F inverse is sine inverse x plus 5 over 3 minus 2. That's how we can find the inverse of a trig function. Okay, now let's talk domain and range real quick. We already found the domain of f of x. And we are going to want the domain of f inverse and the range of f inverse. And we're going to want the range of f of x too. All right, so remember, they flip-flop positions. So you know one, you know the other. We know the domain of f inverse. It's this wacky looking interval up here. Right? It's it would be my x's would be stuck in between negative pi over 2 minus 2 and, oops, except that should be a bracket there, and pi over 2 minus 2, because we include that. So that's the same as my range for f inverse. Okay, now I just need to find one of the others, either the domain of f inverse or the range of f of x, because once you know one, you know the other. Really doesn't matter, but I think the range of f of x for me is personally a little easier, because I think of my transformations here. If I were to graph this function, if you were to think of that graph, one thing I can see is that it's got an amplitude of 3. So my sine wave is going to a max and min height of 3. And then I could see that it's also got a vertical shift down 5. So every one of these points is going down 5. So this point here goes down 5, and it's really going to start at a negative 2. And this point here is going to go, which, oops, I think I had mislabeled. That should be a negative 3. That's going to go down 5 as well, putting it at negative 8. My sine wave, oopsies, it's going to look something more like that. Okay, obviously very crude drawing there, but what I'm looking at is I'm looking at the range, the window. The range of f of x is between negative 8 and negative 2. Well, that is then the same as the domain for f inverse. We get it for free as long as you know one. Okay, I hope that's helpful. Main goal, be able to find the inverse of a trig function, and certainly being able to wrap your head around domain and range is quite helpful as well. Keep up the good work.